Hello, everybody. My name is Pablo Garcia Salaverry, and I am assistant professor at the Department of Thermal and Fluids Engineering at the University Carlos III of Madrid in Spain. And I'm going to present you the work in collaboration with Arturo Sanchez Ramos. We both belong to the fluid mechanics research group. And the title of the work is multiscale modeling of the effect of membrane thickness on the performance of proton exchange membranes towards high performance fuel cells. Okay, so the outline of the presentation is as follows. First, I will introduce the topic, the motivation of our work. Then I will present you the development of a 1D macroscopic model. This will be followed by a parametric analysis and a simplified model. And finally, we'll have some prospects in membrane design and microscopic modeling, and the conclusions and future work. Okay, well, so the proton exchange membrane, as we know, plays a key role in the performance. It is a efficiency limiting factor, and we can, for instance, design better materials for the membrane, but also it is important to analyze the thickness of the impact of the thickness of the membrane in performance. In particular, the thickness of the membrane is going to be directly related with the resistance of the membrane, but it is also going to affect the crossover of the species, maybe the water balance in the cell. So we need to understand simultaneously the materials we put there, but also the impact of the thickness. So that's our main goal in this presentation. Okay, to analyze the thickness of the membrane. So previous work we have regarding the thickness of the membrane. In 2013, we have work from Gore. This was with their ultra thin reinforced proton exchange membranes. Well, as you can see here, in terms of performance, it is good. No, as we decrease the thickness of the membrane, there is an improvement in performance. Obviously, there is a decrease in the resistance of the membrane, but also we can see here that we can reach higher limiting current densities. So this one, the first question is what happens as we decrease the thickness? If there are a couple effects there. When I touch the resistance of the membrane, I am touching at the same time the water balance, the thermal management, all these kind of coupling effects. It is necessary to understand them, and for that we need modeling. Well, in combination with characterization and performance, but modeling plays a key role. On the other hand, we have this is expected, not durability is going to be affected as we decrease the thickness of the membrane. It is necessary to design reinforced membranes that are able to work within acceptable limits with a small thickness. So there is also work to do in terms of how we reinforce the membrane. There are different approaches to do that, but that's something we have to also take in mind for the application. So that's the point. We have some possible improvement in performance, couple effects, durability is expected. So how can we do with this? No, this problem. This is starting with this trade-off and couple effects. So we have, well, we have developed so far a 1D macroscopic model. So it is a steady state model. We have two-phase transport. We have non-isothermal effects. We have some assumptions. We have negligible convection. Also, we assume right now that the membrane is impermeable to gas species. And you can see here the domain. So we have the model for all the components of the membrane electrode assembly. And okay, so we have only one coordinate in our model, say the y coordinate, and we are describing what happens through the thickness of the membrane electrode assembly. In terms of Copernican equations, we have two for charge conservation equation. We have electron transport, and then we have proton transport. Then we have water transport in the membrane. We have diffusion and electrosmotic drag included in the model. Then for species conservation, we have that of water vapor, hydrogen, oxygen. For liquid water transport, we have well, usual approach of considering the lever J function to relate capillary pressure with saturation. So, well, and we have this equation for liquid saturation. Yes, introducing Darcy's law into the mass conservation equation of the liquid phase, we can put this equation in terms of liquid saturation. And then we have the energy equation. If heat transport, we consider only conduction. Okay, so it is the dominant flux there or contribution. So we put that part, the conduction. So well, and then we have many source terms in the model. As usual in fuel cell models, we have those for reaction kinetics. Then we have water desorption and sorption in the catalyst layers. Then we have water condensation and evaporation. And then for heat transport, we have several. We have Joule heating due to proton and electron transport. We have also latent heat due to phase change phenomena. This includes here the sorption and desorption in the catalyst layers. We have also that evaporation and condensation. And then we have the heat for reversible and irreversible heat due to the electrochemical reactions in the catalyst layers. So, okay, so we have all those source terms in the 1D model. And then in terms of boundary conditions, okay, so we have for the cathode channel bipolar plate interface, so we impose the voltage, then we have some inlet oxygen concentration. We consider an air-fit fuel cell, so we have that factor of the 0.21. So then we have also some concentration of water vapor associated with the relative humidity of that compartment. Then we have maybe some saturation at the interface. We have the operating temperature of that compartment, and we have the same, but in terms of here we have hydrogen for the anode terminal. Okay, So the model is implemented in MATLAB. We use this function, which is suitable for 1D models, and well, it is rather fast, and it is easy to implement using this function available in MATLAB. Okay, so in terms of PEM properties, we consider those of Nafion and similar perfluorinated membranes. So we have here we have, for example, the equilibrium water content, the isotherm, as a function of the relative humidity. So we have this dependency with the temperature. Then for the effective ionic conductivity, this is a function of lambda, the water content per sulfonic acid group, and the temperature. Okay, so we have these correlations. They are quite common in the literature. For the electroosmotic drag coefficient, we have this correlation also, which is a linear relationship in terms of lambda. We neglect any possible couple effect with the temperature because, well, this here where you can see experimental data at different temperatures, and there is not a clear trend with temperature. So they are almost, we can say that regardless of the temperature, we have this linear relationship. And then for the diffusivity of water, then we have this expression, which is a function of both lambda and temperature again. Okay, so we have this kind of this increase of the diffusivity with lambda and also with the temperature. Okay, so with this model, it's a perfect tool to perform a parametric analysis. So we have run around 600 simulations. This means polarization curves. We have fixed operating pressure, 1.5 bars. Then also the thickness of the GDL and MPLs are fixed also. The catalyst layer thickness is fixed to 10 microns, but then we consider different thicknesses of the membrane. We have 10, 25, and 50 microns, and we explore the plane here, this combination, temperature ranging from 50 to 80 degrees Celsius, and then the relative humidity is varying between 0.2 to 1. Okay, so we will combine these to see the effect of temperature and relative humidity. The computational time is around 30 seconds per simulation. It is variable, but the average is around that value. And you can actually run this kind of parametric analysis in a desktop, in a good desktop computer. You don't actually need a workstation. This is good for this 1D model. So, well, first we have the result of the parametric analysis. We have the current density. So here you can see the results for the 3 different membranes. And here we have these contours. Here we have the relative humidity. Here we have the temperature. And we are plotting here the current density at maximum power density. Okay, so we have, what we can see is that in particular, there are these differences is that we can reach much higher performance as we reduce the thickness of the membrane at fully humidified conditions, okay, on high temperature, but especially as when we are here, good humidification. But also we reach a better performance at low relative humidities. It is much higher compared to this thickness of the membrane. Here we have only 0.4, and here we are reaching around 1 ampere per centimeter square. So it is something. The first thing we can see is that the ultra thin membranes can improve the performance at low relative humidity, and we reach very high performance at high relative humidities. So operation at relative humidities with ultra thin membranes is possible without having dramatic ionic losses. Okay, so that's good. Why is happening that? Well, what we can see is that, well, first we have the resistance of the membranes. Here it is, for instance, we are using a logarithmic scale. So here for the membrane of 50 microns, we reach very high resistance here at low humidification. Here is even comparable to the one we have with 50 microns. And then when we move to ultra thin membranes, we have this much lower membrane resistance. Okay, so so there's something going on there, no? That there is why at full humidification is expected. We have a lower thickness, so a lower thickness will be better because we have a lower resistance. Here there is some coupling with water balance. And what happens is, if I will look at the water content, you can see that it is almost the same at low humidification. Even well, despite the fact that the current densities we are reaching with this membrane, the ultra thin membrane, is much higher. The current density here is much higher. So, and this is because we have enhanced back diffusion to the anode. Typically, we have a dry out from the anode, and the use of ultra thin membranes has this couple effect of enhancing back diffusion. So we are able to have an acceptable performance even at low humidification. So we have that the amount of water at the anode is comparable to other membranes. So that's good. So because we can avoid the premature drying out of the anode side with these ultra thin membranes. Well, for instance, we can compare the result with a simplified model. Model for the interfaces. We have the interfaces, meaning the catalyst layers. So at the catalyst layer, we have sorption and desorption. Then we have some water production at the cathode. Then we have electrosmotic drag. We have diffusion. If we add both equations, we get the global balance will be some in the the catalyst layer plus the membrane, the water that we produce, which is there is a balance with sorption and desorption at the cathode and the anode. Okay, so but we have two equations with two unknowns, which are the lambdas at the cathode catalyst layer and the anode catalyst layer. In all this formulation, we have assumed that the desorption is infinitely fast. Okay, so okay, so we have this simplified model just to check, not to compare with the parametric analysis. Well, what you can get from this very simple model is that, in fact, well, with the blue lines correspond to the ultra thin membrane. So Yeah, actually, at very low relative humidities, you can reach much higher current densities without drying out of the anode. Okay, this is very different from the other two membranes, and where we observe very high ohmic losses and will be the hydration of the anode. Okay, so because what you can see here, well, that the dehydration of the anode, well, we reach the percolation threshold of the conductivity. So from there, we can no longer have an acceptable performance. So that's good. So the here even we can look at the absorption and desorption. So the main conclusion is that a lower membrane thickness enhances back diffusion. So we can have an acceptable performance at low humidification. So we can, this opens the gate to operate cells at low humidification. So we can have high performance. No? We can reach an optimum balance between mass transport losses and ohmic losses. Because of the water accumulation along the channel, we can decrease that operating at lower humidification. The thin thickness is able to keep to stop there the ohmic losses at those low humidifications. Okay, so that is there is this synergistic effect between water balance and performance. So, and from the experimental side, for instance, we have ultra thin membranes has been used in the Toyota MUA. So they are using a reinforced membrane with a thickness of 10 microns. So that's there. Okay, so these kind of strategies are valid, are valid to reach high performance, combining materials with operating conditions. We have in terms also some prospects for to produce reinforced membranes. Well, we have this approach now with the Teflon introduced the membrane to put there some reinforcement. But then we can also use other strategies. There is one interesting strategy, which is the pore filling membranes, will be to put before the reinforcement and then to add the conductive phase. It's just we are doing the opposite. So with this kind of approaches, it has been reported recently that with, for example, like 6 microns membrane, well, you can see that we are able to do to have high performance at low humidification, something that is not possible with Nafion 211. Okay, and it's very promising this approach of pore filling, because we can reach very high mechanical properties. So this can be a good procedure to have these thin membranes with better performance, but also with very good mechanical properties. Okay, so that's next steps, the synthesis of this kind of membranes with this approach. And also next steps are the modeling, the microscopic modeling of these membranes, of reinforced membranes, using a hybrid continuum pore network formulation. Okay, so that's it is here modeling is going to play a key role to balance the durability and performance of ultra thin membranes. In particular, it can be very useful for the pore filling membranes. So the conclusions of our work is that the interplay between the thickness, water management, and performance is critical for high performance fuel cells. Ultra thin reinforced membranes with good durability and low crossover can be a reality in the near term. It can be the synergistic effects if we are able to have good durability are very promising for the technology. And then, well, further work, we have to improve our simplified model, try to put some analytical solution using Kirchhoff transformation, analyze the role of the boundary conditions to the membrane or the set catalyst layer plus membrane with the, so what is the effect of the micropore layer and the GDL, the impact insertion and desorption, to analyze the effect on performance and durability. Here, it will be necessary to include a 1D plus 1D model. So we have also the evolution of water vapor along the channel. That's a key point there. And then, well, we have modeling and characterization and testing of thin and ultra thin reinforced membrane and microscopic modeling. Okay, well, so thank you very much for your attention. Thank you for watching.